So without dealing further, let's get a brief introduction of transfer learning, what it is. So as we all know, it dates back to decades. Like in 1986, when Tom Mitchell published his first book on machine learning, the idea of transfer learning was laid out there, right? Then in early 2000s, Raina introduced this sparse encoding based pre-training for transfer learning, and at the same time, Ben David as well introduced to us the domain adaptation using generalization bounds, setting the theoretical basis for transfer learning. But the real breakthrough, I guess, occurred during early 2000s when the large transformer models came to play and they revolutionized the whole transfer learning, mostly in NLP and vision. But unfortunately, the tabular data remained the second class citizen. Not until 2023, when it finally started getting its due. One of the notable works was by Levin, who introduced and addressed the feature mismatch across the tabular domains. Unfortunately, they had also one assumption. The assumption was that there will be a partial overlap between the source and target domain features, and which is the most common assumption in the regular tabular transfer learning methods, that there will be some feature overlap or semantic alignment between the source and target domain features. But in real world setting, this might not happen. Datasets can be completely heterogeneous, no feature overlap at all. And regular transfer learning methods are unable to handle that. No prior work has been able to tackle this kind of heterogeneity, able to transfer learning across this kind of heterogeneous datasets. And we present ModelX, which is to our knowledge, is the first one to enable transfer learning across the datasets where the features do not overlap at all. We demonstrate that meaningful knowledge can still be transferred even when the domains look structurally unrelated. Why we are emphasizing that? Because transfer learning works best when the domains are aligned, right? Which means same set of features, same set means same number and types of features as well as data distributions. But in reality, the assumption is so fragile because mild distribution shifts and as well as labels per city can dictate the transfer learning performance. And then regular transfer learning methods assume that to be able to effectively transfer knowledge, there will be a common feature schema across the source and target domains. But that may not hold true in practice. Actually, in HPC workflows, that is the norm because data is independently collected, right, across the platforms by different users and instrumentation setups. And thus, what we see is that when we collect data, that data may have the same feature but with different name, or maybe the feature may be totally missing, even if we are collecting two applications on the same platform. And from what we can see is that we collected COMD and CryptK on the same platform, but they have totally disjoint features. And even if they have one same feature with different name though, but then it has completely different distributions. And all this actually makes the alignment or the transfer learning doubly hard. So as we have seen so far, what is the problem with transfer learning, how this heterogeneity comes to play? In the next few slides, we will discuss more or a little about why this heterogeneous transfer learning occurs during the HPC scenarios and how our ModelX helps it to solve the problem. So the heterogeneous transfer learning in HPC can occur in three broad categories. Let's say for us, we are interested in performance modeling, and if we want to predict performance of one application using another application's data collected on the same system, there can be heterogeneity and we name that as cross-application scenario. And then we might be want to know one application's performance on, let's say, GPU based on its data collected on CPU, and we name that as cross-architecture want to know one application's performance on one system collected on another application's data on another system. So in this work, we solved the first two. And as we have already told so far that regular transfer learning methods do not work out of the box. Then what others do to solve this in these scenarios? They extensively collect data in the new scenario and rebuild the whole model, which can be expensive. Or they assume that the mismatch is only in the feature names and they manually align the data, which can be infeasible and requires domain knowledge. Or they assume some form of feature overlap, which also may hold not true in practice. In this work, we want to remove all these barriers for effective transfer learning. And this slide tells you or shows you a top view of our whole ML modeling pipeline, how we do so. In our ML modeling pipeline, we collect data from different layers of the ecosystem. So, and after collecting all this data, we build a model using our standard machine learning based pipeline. After building this source model using all this data collected so far, we go to the inference phase where we do the test time adaptation. What is test time adaptation? It is basically adapting the source model using the few short label samples from the new scenario, and then after successfully adapting the source model, we then successfully leverage that for prediction on the unseen label samples. Now, regular transfer learning methods do not work when the domains become heterogeneous. And what are the regular transfer learning methods? The most common transfer learning method is to build a model on a dataset and then use that model to predict without doing anything, which basically known as the zero-shot adaptation. Or maybe you can update some of the layers and keep the rest of the layers frozen. We all know which is known as the linear probing. Or maybe we can update the whole model, which is known as fine-tuning. Now, none of this, the linear probing or fine-tuning, works when there is data heterogeneity, which is feature mismatch across the source and target. How our ModelX can solve that? Specifically, what we do is, after building the source model, we take the few and new label samples from the new scenario to train a feature extractor model, which is basically a fully connected neural network. And then we take the output of that fully connected neural network feature extractor and pass that to the source model to make predictions on them. And then when source model makes the predictions, we use the loss calculated from those predictions to update the feature extractor layers, which happens all within this blue box. We name this blue box as input alignment model. But what if there are some features that the source model never saw? How do we do that? We use residual model to handle those residual features. The residual model handles the unseen features by the source model. It learns the relationship between the new features and matrices from the target domain. Last but not the least, we use a comparator network, which is ModelX, which basically learns to pick which network works best with one data set during inference time, and it takes both the input alignment model and then the input alignment model augmented with the residual model that is being trained with the few samples, and learns which model works better with one set of data, and then it makes the predictions. And then during inference time, we need not to worry at all. The ModelX picks whatever model works best for the data and leverages that to make predictions. Now, as we have seen, there are three key components in our ModelX, which is the source model, the input alignment model, and the residual model. A user actually does not need to worry about any of this because ModelX picks and does all of this automatically. But then still a user may want to know when and why each of these works better, when input alignment is sufficient, and maybe why and when the residual model is necessary. To aid in helping to explain why each of these steps work better, we propose a novel measure to quantify the divergence between these heterogeneous datasets. To quantify the divergence between these heterogeneous datasets, the first question we solve: what if the number of features don't match during this divergence calculation? And the answer is straightforward. We do a PCA which solves this problem of dimensionality reduction as well as homogenizing the features. The second problem we solve is: what if the number of samples do not match? We leverage the synchron optimal transport method, which learns probability distribution from these data sets and solve this problem of number of samples. And then lastly, we use our existing method of distance calculation from a previous publication, which leverages Grassmannian manifold to learn distance from two subspaces by measuring principal angle between the principal components within which the information resides. The higher the angle is, the more divergence between the information there is, and the more severe the case of transfer learning it is. So a low severity means there are less hurdles for transfer learning, and from all our experiment with 15 data sets, we have seen so far that the severity value lies from 0 to 0.7. This slide tells us the two different scenarios we have evaluated our ModelX's applicability so far. One is online and the other is offline. During offline scenario, we used ModelX to pick source and target dataset descriptions from a config file and then to do the prediction business there. For an online scenario, we plugged our ModelX into a job scheduling simulator where the simulator scheduled jobs using ModelX. How it leveraged ModelX? It used ModelX to make predictions for the runtime, and that way it scheduled the jobs. And also, after getting some of the matrices running the job so far, it updated the jobs using those matrices in real time. So this slide basically also tells you how you can use this ModelX in both of the fashions, both online and offline. And the next slide, we are going to see how ModelX fared in all those evaluations. Before going into deep about our results, here is a quick look at which datasets we have used so far. As I have said, 15 datasets, from which 11 are HPDC datasets, which is a mix of different proxy applications collected on various platforms, and they consisted of different number and types of features altogether. And for each of those experiments, we actually crafted the target column carefully. We haven't used same target for all of them. Let's say for cross-architecture experiments, we used parallel efficiency loss as the target column, and then maybe for some of the cross-application scenarios, we used runtime and other matrices for the target value as well. And then we also, for the sake of generalizability, we used for machine learning, standard machine learning datasets, I would say, as well, to prove our proposed method's generalization capability. We have seen what we have seen in all these experiments are coming in the next slides right away. One point I would like to let you know that we measured our model's effectiveness using mean squared error formula, but the input to that mean squared error formula was the ground truth value and our ModelX's predictions for sure. So the next slide tells you more about our ModelX's performance on cross-application scenario, where we try to predict one application's performance using another application's performance on the same system, basically. And then we can see there are three regions, right? Green, yellow, and red. So in the green region, as you can see, the severity value is lower, and that's because the source and target belong to the same data set, which means actually they are coming from same distribution. So no distribution dissimilarity at all, which means no severity at all. And for that reason, source model was sufficient there to effectively transfer knowledge. No other extra modeling was necessary. But as you can see, for yellow and red regions, the severity value is higher. That's because all those cases there were some distribution dissimilarity. Now for yellow region, those are the cases that are homogeneous, which means though the features are the same across source and target, the dissimilarity arose from distribution shift and level sparsity. But as we can see there, our model X was sufficient enough to handle all of that and to efficiently transfer knowledge. From the standard state-of-the-art methods, only linear probing performed better there, but as we can see, our model X has this mentioned improvement over the best state-of-the-art method, which was linear probing, of course. But then, as you can see, the red regions, those are the heterogeneous regions, which means source and target did not have the same number and types of features. And I want to highlight the fact that no state-of-the-art methods were being applicable there, or no state-of-the-art methods were being able to be leveraged there. Only our model X was being able to transfer knowledge in those scenarios and also with improvement. Now, what is the model we have calculated our improvement with respect to model X? So what we did there is that we took the few short samples that we are treating as available during inference time, and we built a model from scratch using those few short samples, which we named as retrained few shot. And what we see here is that our model X achieves improvement over that retrained few shot from 95 to 99% and 93.5% on average. So I would like to say this is a feat over the regular state-of-the-art methods, as they cannot solve the case where model X can does, and that also is victory. The later slide shows you the case where we transfer knowledge across the architectures, and not to say the architectures are completely different. The example we are seeing here, that is data collected from Access Bench application collected on two different platforms, IBM BGQ and Intel Centrifuge, which have completely different number and types of features. Though the platforms here are a little bit older, but we bringing this point here for the sake that we want to show how much the platforms dissimilar are. Our model X can effectively transfer knowledge across those platforms. And as we can see, the blue bar here is the model X, which gives you the lowest error in terms of MSC lesser than 0.2. The other models we compared here is the retrained feature, which I just described, is the orange one. And then we also compared our model with another model, which is the green bar, which is a kind of oracle model, which is a supervised model with 26 times more data from the target domain. But our model X still outperforms that because it is being able to leverage the source applications knowledge, and as well as it is being able to generalize to the test domain well. And it also shows the lowest error margin. This is the scenario where we evaluated our model X with online job scheduler, and I just wanted to highlight the key points that it achieves 3.3 times faster turnaround time. The red line is the regular scheduling scenario, where the green line shows our proposed scenario, and as we can see, the regular scheduling method needs 45% more resources to achieve the same amount of turnaround time. So I would like to leave you guys with two key points. The key point I would like to highlight is that Model X fills a core gap in machine learning. It enables transfer learning across fully heterogeneous tabular domains, but that's not it. It's more about making machine learning practical and usable for high performance computing. For too long, it has been on the margins of machine learning innovations, right? left out because its data is too messy, too fragmented, too different. With Model X, we bring machine learning to HPC on HPC's terms. That means learning from real world data, handling heterogeneity head on, and unlocking the true potential of scientific computing at scale. Thank you so much.
So, question, please. Question.
Have you tried your ModelX on same machine over time? So let's say Intel i5 and like that, or maybe for NVIDIA, the same GPU, but the GPUs keep on increasing over time. So have you tried that ModelX is able to adapt those changes and able to predict the performance for a newer architecture with only 1 or 2% of it?
Actually, yes, we have evaluated with a lot of data sets, but we have not included all of them for sure. So yeah, we collected data on the newer versions of AMDs, and then yeah, MI100, MI150, and we also evaluated with all those. But you know, for the sake of the paper spacing, we have not included all of them in the paper, and then time was also lesser, so we have not included here as well. But I can surely discuss more about these results with you for sure, because we have evaluated that. And yeah, we have evaluated not only ModelX but a better version of ModelX as well, which we plan to bring on future. But thank you so much for the question.
So what are you predicting exactly, like
So
execution time?
thank you so much. Yeah. So as I said, for different experiments, we are predicting actually different things. Let's say for cross architecture, we are predicting parallel efficiency loss, which we actually kind of described in the paper. But then maybe for predicting performance of two applications on the same platform, maybe we are more interested in the runtime or any other metric, because those two applications are belonging to the same platform. So it will make more sense, right? To know if one application has run that amount of time, how much time the next application is going to take. So for that, some of the cross application scenarios we used runtime as a metric and similar matrices as well for target column. But mostly for cross architecture, we used the parallel efficiency loss.
I have questions. How, like more like in details on how the ModelX bridge the structural heterogeneity? Is it like, are you also like applying some sort of filtering inside this model? Because that, I think like that's how we usually like do transfer learning, like to reshape like the data sets. And my second question is, I wonder what happens if like the severity measure is like really high, and then does that mean like the model will not be able like to predict the good results, and it will inform us? It's because like yeah, it's just like too diverge.
Thank you so much for asking the question. I would love to answer that. So let me answer to the first question. So yeah, we do not filter anything. That's the beauty of ModelX, you know. So our whole assumption is based on the fact that if the data, the underlying generating function of the source and target data is the same, then there should exist a learnable transformation function that will transform the target data to the source data in forms of a learning mapping function, a learnable mapping function, I would say, given the fact that the underlying data generating function is same. So how that can happen? If, let's say, for example, we are running one application on two platforms, there should be some underlying similarity because we are running the same application, right? That is the assumption behind our work. And because of that, actually we do not do any filtering. We just want to learn what is the global transformation function that is behind that. And we empirically proved that there is a way we can learn that function, you know. And yeah, I guess that answers the first part, right? That there is no filtering actually. We just take the whole data, no filtering at all. Though there is basic pre-processing which happens in the machine learning phases, you know, data normalization and all, but no other filtering, and then we predict or learned, our input alignment model actually tries to learn that transformation mapping function, a global transformation mapping function. And the second thing is, that is a very good question, because severity can rise. So if you notice, there are three scenarios, right? Cross application, cross architecture, and cross application, cross architecture scenario. So initially we begin our experiment with all of them, but later then we realize that the cross application and cross architecture is harder one, because if for the cross application and cross architecture we can visualize from where the underlying function is coming from, right? If we run one application on two architecture, we can visualize this application is running on the two devices. If we run two applications on the same platform, we also can visualize how this underlying function is coming from, the one unified underlying function. But for one application on one platform and another application on another platform, to find out the common underlying function is super hard. And in those cases, we expect the severity value to rise. And our ModelX does not, we have not evaluated our ModelX's capability on those scenarios, because we cannot fully explain the underlying function there. But yes, we hope that we actually have seen and hope to see more that our severity value will be higher in those scenarios, and we still need to run and find a better solution for those cases.
Yeah. Let's, in interest of time, let's thank the speaker and go to the service.